Hey guys, this is Mrs. Clay. We're going to see how this works out, but I'm hoping that I'm going to be able to record some of my presentations or slides for you guys more often. So if you are absent due to illness or something, that you can still stay on top of the class other than have you check Canvas. So with that, you can see my screen right here. To the right is Smart Notebook. So what I'm hoping to do during this is I'll write some stuff down, maybe some sample problems, and then to the left I have the actual presentation that I use for class. So we're going to click present real quick, and then when we start doing example problems, we will go to our smartboard to help us with those answers. So pause whenever you need to. I'm just going to kind of keep rambling on because I do have a time limit on how long these presentations can be. But we're going to be writing formulas and names for simple salts. Now you're going to need a periodic table, notes, pen and pencil to do this because you'll be writing problems, and you'll also need to see what elements we are working with. So take a minute to pause this to pull out those things, and then we're going to move on. Okay, so salts. What are salts? The most common salt that you guys are familiar with is table salt. It looks like this, unless you get a different brand, that's fine. But whenever you're eating dinner at the dinner table and you want some more salt on your pasta, you say, "Pass the salt, please." And what you're referring to is this type of salt right here. Now, you don't know this quite yet, but there's actually a different salt that you use when you're cooking, and that is baking soda. These things are not normally considered related, but actually in the world of chemistry, these are both considered salts. We're going to talk about what that means on the next slide. But baking soda, the real name for this is actually sodium bicarbonate. The real name for this salt to the left is sodium chloride, and we're going to see what they have common in a minute. Now, I do want to say that this would be a great April Fool's Day joke if you were by chance to make some cookies. Instead of maybe putting baking soda in it, you just put the salt to the left, and you'd be able to say that you put salt in there, you just weren't specific enough about which salt you wanted. Okay, enough with the terrible jokes, let's go on. So before we get started, we need to review ions because that will help us figure out what salts are. Metals are, when they become an ion, they need to either lose or gain electrons. And metals, if you remember, always lose electrons. Okay, I had you write down somewhere, metals always lose. If you want to think of a different way to say it, you can say they donate their electrons. They're practically giving them away because they have excess electrons. When they get rid of these electrons or lose them, they start to have a positive charge. Now, a positively charged ion has a name, and we call it a cation. You'll notice that the T looks a lot like a plus sign, and so we can do that there. Okay, cations are always positive. Now we have nonmetals. Nonmetals are the opposite of these, so they accept electrons, and doing so, they become negatively charged, and so we say they form anions. Now, metals and nonmetals together create what we know as ionic bonds. So ionic bonds, and these ionic compounds, we call anything that has ionic bonds, a metal with a nonmetal, to be known as salts. So that's why in the previous slide when we talked about sodium chloride and sodium bicarbonate, both of those have a metal and a nonmetal in them, and they are forming ionic bonds. So with that, the idea of salts all of a sudden gets really broadened because we have probably 40 some odd metals on the periodic table and 20 some odd nonmetals on the periodic table. And so we can get a lot of combinations, and these are all called salts. Well, how chemists work is they have a set of rules for writing and naming these formulas, so they can come up to someone and say, "I want barium chloride," and they know exactly what they are talking about. So with that, let's learn the rules and names. We have, before we get started too much, I want to talk about what chemical names and formulas do for us. Now, they represent the chemical compounds, but more in particular, they give us two types of information. The first information that they give us is composition, what these things are made out of, and then they also give us what I'm going to call a ratio. Okay, so two types of information, composition and ratio. I'm going to pull up an example, and I want you to be able to pause the video after each example and try to figure out what these things are composed of and what are the ratios. Okay, So our first example is big M, little g, big C, little l to the 2. Take a minute and pause this. What is the composition and ratio of this? So Mg, the abbreviation for Mg is magnesium. So we could say that this compound, MgCl2, is composed of magnesium, and the Cl right here stands for chlorine. So this has magnesium and chlorine in it. Now the ratio of this, we have to look at what subscripts we have written down. Magnesium does not have a subscript, but because we've written it, we know that there is one magnesium. If there wasn't any magnesium, we would have not written the abbreviation in the first place. So if there's one of them, you don't need a subscript, and you're just going to write the abbreviation. Now, how many chlorines do we have in this? Just look at the subscript over here. We have 2. So 2 chlorines, 1 magnesium make up this compound. Let's do another example. What is this one composed of, and what is the ratio of these atoms coming together? So Al is the abbreviation for aluminum, so we have aluminum in here. And then O stands for oxygen. We have aluminum and oxygen in this compound. And you'll see with the subscripts, this tells us that we have 2 aluminums for every 3 oxygens. Okay, so those are the ratios. Let's do one more. Now, what is this thing made out of? Well, we can see the word calcium, but sulfide. I don't see sulfide on the periodic table. We are going to find out today that this actually has a rule involved. We drop the ending of nonmetals and add "ide" to the end. So this actually contains calcium and sulfur, and we'll find out today why we drop it and add "ide." But this is how we would write it. We know it has calcium and sulfur in it. Now the ratio is not as specific or as out there as these other examples. When we write the formula, we have these subscripts that indicate how many there are, but when we have the name, we can actually figure it out. We just have to take a minute to solve it. So the ratio is still found in here, it's just not directly written out. Okay, so with all of that, let's talk about some general rules for naming and formulas. So this is common throughout names and formulas. The first rule I want to talk about is you always write the cation first. Now remember, cations are metals that are ions. So you always write the metal first because that's always the cation. Another rule is the cation name does not change. We do not change the ending. I'll have a couple examples over here to tell you what not to do, but the name doesn't change. You can get that right off the periodic table. Another one is if it's a transition metal, add a Roman numeral. And then the final general rule is that the anion name, so whatever's the nonmetal, you are going to drop the ending and add "ide" to the end. Now I didn't really explain, if you noticed, the third bullet point down about transition metals, and that's because we haven't really touched on transition metals in this class. This is going to be something that we're going to talk about in the next couple of slides. My classes actually only got until right before we talked about Roman numerals, so I'm probably going to make a different video about it that will continue on with these slides. But if you want to and you're curious, you can look in the couple next slides and you can figure out Roman numerals for yourself. Okay, so to the right we have this red line right here. It's just going to divide between what would be the incorrect name and what would be the incorrect formula. So if I were to break these rules and not follow them, this is what I would have written and this would be wrong. So if we did not write the cation first, meaning we wrote the nonmetal first, we would say chlorine, sodium if we were talking about table salt, which is down here. So chlorine, sodium, for me, that just sounds wrong, but I'm a chemist, so these are just rules that you guys will have to get used to. But you always say the metal first and not the nonmetal. Now, if we wrote the formula wrong too, it would say ClNa, not NaCl like it should. Okay, cation name. If we decided to change the ending of this, we would look at something like sodide and chlorine. Sodide chlorine just sounds wrong. Don't do it. It's wrong. And then this is not applicable to the formula because we don't write out the whole name when we do the formula. Like I said, we'll talk about Roman numerals later, but sodium is not a transition metal, so we don't even need to worry about that step. If we by chance wanted to put a Roman numeral, it would be wrong because sodium is not a transition metal. Sodium is found on the periodic table in group 1, which is the alkali metals. The transition metals are ones that we have not talked about very much, and so we'll have to explain that further next time. Now the last one, what not to do. You do not just say sodium and chlorine instead of sodium chloride. That is not the right answer. The right answer is sodium chloride. So what makes the difference between it ending in what it should on the periodic table compared to dropping the ending and adding "ide"? Well, if you're having a conversation with someone and you say sodium and chlorine, you are talking about those as individuals. So you're saying sodium is this, chlorine is that. Well, when you drop the ending and add "ide", you are now saying that these two things are bonded together. We need to look at it as a compound instead of as individuals. So you really need to add that "ide". That is very important. Okay, so writing formulas for simple salts. Let's write out the steps. The first one is write the abbreviations of the element. Okay, so if you have the name, you can look up what abbreviations those have. Then the next one, step number 2, you determine the charge of the ions. You have to look at how many valence electrons it has, how many does it want, and in that process it gets this charge. So we need to find out what that charge is for our answers. Step number 3, hopefully this sounds familiar. This was on our last test at the very end, but you need to find out, now that you have the charges, how many you need of each ion to have an overall charge of 0. And then finally, now that you have all the information, you can actually write the formula and use the subscripts to indicate how many you need of each ion in that compound. So with that, I am running low on time. I only have a couple minutes, so I'm going to go through this fast. Pause it if you need to. So we're going to do lead oxide. The abbreviation for lead is Pb, and then oxide. Oxide's not on the periodic table, so what is it? Oxide is actually oxygen. Remember, we dropped the ending and added "ide", so it's going to kind of take some getting used to, but oxide is standing for oxygen, and its abbreviation is O. So now we finished step 1. Step 2, we need to look at how many, or the charge of what lead's going to be. So let's get out of, actually no, we're going to have to keep, yeah, why not? It might not let me. Okay. So let's do this real quick. Oh, it shows the answers. This is not going to help. Okay, so lead right here, it says it has a +4 charge. Let's figure out why. Lead, it has 4 valence electrons because it's in the 4th group. It wants to have 8 electrons, so the question is it going to gain 4 to have 8, or is it going to lose 4 to have 8? Well, metals always lose. Lead is a metal, so we're always going to lose 4. If we were to convert that into a charge, we would say +4. So that's how we get that +4. Now oxygen has, let's go through this, 6 valence electrons. It wants 8 though, and so it has to gain 2 in that process, so it's going to get a -2 charge. Now this needs to balance out together, so what we're going to see is if we take one of each of these, one lead and one oxygen, we'll notice that we get an overall +2 charge. Well, we don't want a +2 charge. Let's write it out real quick. Lead +4 and oxygen -2. If we were to add the charges together, they would equal +2. Well, that's not 0. Our rules say we need to equal 0. So if we're too positive, let's add some more negative in there and see if we can get it to be 0. So let's add another oxygen. Oxygen has -2. Now we have -2, -2 +4. This now equals 0, and we can see that for every 1 lead, we need 2 oxygens. So we're going to go back here, say that we need 1 lead and 2 oxygens to have an overall charge of 0. If we were to write the 1 and the 2 as subscripts, we would not write the 1 because it's already implied that it's there and that we have 2 oxygens. So that's the answer for that. I'm running low on time, so I can't do these ones, but the key is online. You can work through these or ask me later. The answers are these. I'll go through them real quick so you don't get confused too much. But I am out of time. I will make another video to do the names for simple salts, but this is actually where we ended in class today.